Hi, we're back to talk about internal line boundaries this time. And internal ones lie within the area of a domain, not on its external perimeter like external line boundaries do. And there are several kinds of these, and we'll go through the different boundary conditions that you specify, how they're applied, and how you can check their accuracy. And we'll also talk about line dipole and line doublet elements, which are what are employed for three of these different kinds of internal line boundaries. And we'll look at the outputs you can generate for rivers and head specified line boundaries that list discharges and group them. And we'll give some advice about how to model an injunction or pumping trench and how to model rivers. Here's our table of the various kinds of line boundaries in Anaqsim and what sorts of elements they use and whether they're external or internal. We've already looked at the head specified line sync when we talked about external boundaries. That's also an internal type of line boundary if you want it to be. And then these last 5 rows are new features different from the external line boundaries. And we'll go through each one of those in order. Here's the head specified line boundary internal, which is just like the external head specified line boundary we discussed in the previous video. And the example that's shown here has a specified head of 120 at this end, and I think 115 somewhere to the right of this screen grab plot. And there are 3 parameters per line, so there are 3 control points, these little X's, 3 of them on each line segment. And the heads at this particular first control point isn't 120, it's a little bit below that because of the interpolation from 120 at the very end down to something below 120 at that control point. This is a check of the accuracy of one segment of a head specified line boundary in that previous model. And in fact, it's the uppermost segment that starts with a specification of 120 at the upstream end. And the red in this plot is what was specified. Here's that linear interpolation along the line element. The blue is what was achieved in the model. And remember, there were 3 parameters per line, so there are 3 places here, here, and here where those control points are and where the modeled head is exactly equal to the specified head. And in between those, it's approximate, but a pretty close approximation. And in many cases, you can get reasonably good accuracy with just 2 or 3 parameters per line on these things. This is a discharge specified line boundary where you input the total discharge of the polyline, and Anaqsim spreads that discharge out in a uniform way so that the discharge per length is the same everywhere along this polyline. And it's handy for recharge trenches or pumping trenches. It doesn't generate any equations because you know the discharge up front. And each element is got 1 degree of freedom, so 1 parameter per line because it's a constant rate along the line. In this model here, this trench is injecting water, and you can tell that because the V's in the contours point downstream, as opposed to something like a gaining stream where the V's point upstream. This is a normal flux specified line boundary internal. We had these for the external line boundaries as well, but when you do it for an internal line boundary, the underlying element that you're using is a line doublet. And a line doublet has no discharge whatsoever, and it is basically a dipole integrated along a line with the axis of the dipole perpendicular to the line. And we'll explain that in the next slide a little bit. It's very handy to use for impermeable barriers, like the model at the right, where it is set at 0 specified normal flux impermeable. The specified normal flux is met perfectly over n intervals, where n is your parameters per line on each segment. In this one on the right, we're using 6 parameters per line, and we're getting a pretty nice flow pattern around this barrier, which is kind of horseshoe-shaped flow coming like this, going around, and very stagnant in the interior of it. A line doublet element results from integrating a point dipole along a line with a dipole oriented perpendicular to the line. And a dipole is the limit as a source and sink of the same magnitude approach a point. And there's no net discharge for a dipole or for a line doublet or line dipole element. It creates a discontinuity in the potential, which is shown red on the plot here, but the stream function, which is blue contours, is continuous across this. That's just what you want for an impermeable or leaky barrier where you have a discontinuity in head or potential, but you want continuity of flow through it. Even if it doesn't leak anything, you want that continuity, or if it leaks a bit, you want that continuity as well. So these are used for the specified normal flux internal boundary and for the leaky barrier boundary. The strength of the element is the jump in potential, and that can vary along the line depending on the number of parameters per line you've chosen. And you can see at the tips there are vortices, and they tend to cancel each other out where these are strung together into a polyline of abutting segments. So it's still there, a little bit of a tiny vortex, but it only has a very local impact and doesn't really affect the flow pattern in the vicinity, the greater vicinity. This is the check of accuracy for an internal normal flux specified boundary. In fact, that model 2 slides ago with the horseshoe-shaped impermeable barrier. And you can see here that there are deviations along it, but the magnitude is fairly small. And in fact, a couple of 1 to 2 orders of magnitude smaller than the magnitude of the ongoing discharge outside of the barrier. So even though it looks small, large, it's not that much. And the errors that you get are local. And remember that this is getting perfect continuity of flow, or basically achieving the specified normal flux exactly over 6 intervals within this one line segment. This has 6 parameters per line. Here are the inputs for a river line boundary, and you input values of each of these 3 things at the start of the polyline and at the end. First is the stage, which is the elevation of the river surface, the water surface there. The second is a conductance for the resisting bed that is presumed to underlie the river, and it is the vertical conductivity of that bed times its width, horizontal width, divided by its thickness d, perpendicular to the channel, that vertical. And then the last thing is the elevation of the base of that resisting layer, as shown by this elevation here. And that affects whether or not the river boundary condition transitions to a different mode in a drying up scenario. So the equation that's satisfied is right here. The discharge per length is proportional to both that conductance factor and the head difference between the head and the aquifer, which is H, and the river stage. And that condition is enforced at n control points per line segment, where n is your parameters per line. For river line boundaries, you have 2 options in the input. You can check a box that says that this river segment will dry up, and that would be appropriate if the stream is quite small and would dry up if the aquifer head dropped below the stage, the specified stage. Or you can leave dries up unchecked, in which case there's a possibility of flow from the river back into the domain when the head falls below the stage. And this graph here shows how the discharge between the river and the domain works for those two options. So the solid blue line here is with dries up checked. So there will get to be more and more discharge the larger the head difference between the head and the domain and the stage that's specified. So that's just linear and proportional to our conductance factor. And in the case with dry up checked, if you reach a zero head difference, you get zero discharge per length for any head below the river stage. Okay, so aquifer head on this axis, and the discharge per length into the river on the y-axis. If you leave the dry up option unchecked, then you go according to this red dotted line. Same thing when head is above stage, but when you start getting below stage, the discharge will reverse and become negative and go into the domain rather than into the river, up until you reach a point where the head equals the base of the resisting bed, that elevation, and then you get a perch condition. If the head drops any further, it doesn't matter, you get that same discharge. Okay, so that's how that dry up unchecked option works. When you check a river boundary condition, you're comparing the modeled discharge per length along the length of the segment and comparing that to the head minus stage times the conductance factor. And these things are identical at control points, but are approximate in between the control points. So on the left, this plot shows one segment with two parameters per line, and you can see the two crossings where that discharge per length is perfect. And then in the same model and the same segment, we've increased parameters per line to 3, and it matches at 3 places, here, here, and here. And it turns out that the desired or ideal distribution is quite nearly perfectly parabolic, so n equals 3 does a terrific job of approximating the required discharge, whereas linear with n equal 2 is quite a bit less good. Here's a model with a drain/fracture line boundary. And this kind of line boundary is internal, and it makes use of a line dipole element, which will be explained in the next slide. There's zero net discharge, but what it does, it conducts discharge along its length. And the discharge in the drain is proportional to the head gradient along the drain and proportional to a conductivity term, which is B, which is the width of an actual drain, times its hydraulic conductivity, and the discharge within the drain is proportional to that conductance factor. And it's assumed that this drain fully penetrates the domain. So if you want to simulate a partially penetrating drain, you'll need to do a multi-layer model in general. A line dipole element is the result of integrating a point dipole along a line with a dipole oriented parallel to the line, as opposed to a line doublet where it's perpendicular. There is no net discharge both of a dipole and of this line element, and this one creates a discontinuity in the stream function, which is blue in this image, but the potential, which is red, is continuous. That turns out to be just right for a fracture or drain element. And the strength of one of these elements is the jump in the stream function, which equals the discharge that's being conducted within the drain. And that can vary along the line irregularly depending on the value for parameters per line. There are singularities at the tips, which are point sinks in this case, as opposed to vortices. And they, like in the line doublet elements, they tend to cancel out where there is a polyline of abutting segments. and these little sinks, sources and sinks at the tips of elements tend to cancel. This is a check of the drain boundary condition from that model 2 slides ago that had a drain running left to right. And what it's comparing is the modeled discharge within the drain to a fictional discharge that would be computed from the specified drain conductance and the gradient of the discharge potential parallel to the drain. And this is essentially the boundary condition equation that is applied at the control points. So these two will always match at the control points. In this figure to the right, we have n equals 6, so there's 6 places where those two curves intersect perfectly. And it's a little hard to tell where they are in here because the curves are on top of each other, but here are the final 2 crossings right there. And this again has singularities at the tips which tend to cancel one another out when you superimpose the adjacent elements, and the impact of those singularities tends to be very local to the vertex and of no consequence to the larger scale flow field. In the model here, I think the segment I was looking at was in the downstream end of the polyline that represented this drain, and you can see that the modeled discharge is decreasing from a bit above 100 to a bit below 100. And at the lower half of this drain, that makes a lot of sense because the peak discharge within the drain is about in the middle, and upstream of that it's gaining water from the domain, and downstream of that it's losing water to the domain. So that's why the discharge within the drain is decreasing as we near the downstream end of this thing. This is a leaky barrier line boundary, a bit like the impermeable specified normal flux equals 0 line boundary, except that we're allowing that this barrier isn't perfectly impermeable, and the discharge through it is proportional to the head difference across it and proportional to a conductance factor, K star over B, where K star is the horizontal conductivity of the material in the barrier, like if it's a slurry wall, and B is its width. And if you're doing sheet pile walls, you have to come up with this conductivity based on manufacturer's recommendations and so on. So this again uses line doublet elements like the specified normal flux boundaries, and these have no net discharge, and the normal component of discharge is proportional to the head difference across it. This is a check of the leaky barrier boundary condition for one of the segments in the model of the previous slide, and it compares the modeled discharge normal to the boundary to one that is computed based on the conductance and the jump in the discharge potential across the barrier. These two match at the end control points along the barrier, for example there and there and there. So this has got n equals 6, and the others are here, here, and here. And it does a nice job, but again, there are singularities at the tips that make this hand-computed one look different from the modeled, but that again is a very local effect that has minimal impact on the bigger picture. And you can check this by increasing and decreasing n, the parameters per line, and you will see little or no change in the overall patterns of flow and head. Anaqsim has some nice features for looking at outputs of these internal line boundaries, and specifically the discharges of internal head specified boundaries and river boundaries. In the upper right here, I'm showing the outputs of simulated discharge for different river reaches, and these are the individual river reach discharges. You can also group these into groups of river reaches and tally the total among the groups. And this is handy for getting the total discharge above a stream gauge, for example, and comparing to the stream gauge value. In a transient model, you can also get graphs of the discharge versus time at a river boundary or a head specified boundary. Both of those things are quite handy. There are several ways to model injection or extraction trenches. I'll run through the three primary options here. One is with a head specified line boundary. This is where you maybe don't know the discharge you're going to need to achieve a certain head. Very useful for a dewatering system, for example, where you know the head you need to achieve, but you don't know how much it's going to take in the way of discharge to achieve that. And this could also be used for a mounding study for a leaching field. For example, how much can I inject before I'm going to achieve a certain head? The second option is a discharge specified line boundary, where you specify the total discharge and it spreads it out along a polyline at a constant discharge per length all along that boundary. The head won't be constant along it, but that may be the right thing if you're injecting water into a pipe above the water table and you expect it to come out of that pipe at a fairly uniform rate along its length. The third is like the second, but you add a conductive drain right on top of the discharge specified line boundary at the same location, same vertices and everything. And what this will do is the drain will redistribute the flow along the boundary so that if you use a very high conductance for the drain, it'll make it roughly a constant head along the line. And this could be very useful for an injection trench that's super permeable or has a large diameter pipe and it's in the saturated zone. So you think that it would have roughly a constant head. Here's a comparison of the final two ways in the previous slide. On the left is a discharge specified line boundary where the discharge per length is consistent along it, but as you can see, the head varies along it here. And on the right, we've done the same, but we've added a highly conductive drain on top of that discharge specified line boundary so that it now is a constant head and the discharge per length varies quite substantially along it. You can see that just based on the head contours and how much they change as you go across it, that we're getting a much higher discharge per length down at this end compared to the middle or this end. Here are three ways you can model rivers in Anaqsim. The first is the most basic. You use a head specified line boundary and there's no resistance between the river and the domain. The head you specify is what is achieved in the domain. It's not necessarily the river stage, or if it is the river stage, it's exactly equal to the head in the domain underneath it. This never dries up and it never becomes perched. So if the head in the domain falls low enough, then the river supplies water to keep the head up. Second option is to use a river line boundary, which is more designed for this purpose. And there is resistance between the domain and the river. And if the head falls below the river stage, there are two options. It can either dry out and cease to supply or attract water, or it can become perched and continue to supply a bit of water to the aquifer. Both options 1 and 2 are line boundaries that have no width. The third option uses an area sink, area source or sink, a spatially variable area sink, to simulate discharge to and from the top of the domain based on the head difference between the domain's head and a specified top head and the conductance of the upper half of the domain. We'll get into this in a little greater depth when we get to the video about top and bottom conditions. Here's a model that uses the last two ways in the previous slide for representing a river. The upstream end is this hot dog shaped area outlined in green, and it's a separate domain, and it has a width. And inside that domain, there is a spatially variable area sink that lets water out of the domain and up into this reach of wetland or river based on the difference in head between the underlying domain head and a specified head along this wetland or river. And that specified head can slope and have a curve to it, or it can be constant. And like I said, we'll get to that later when we talk about top and bottom conditions and spatially variable area sinks. If we did that and we examine the vertical discharge in and out the top of the model across this yellow line, we could see this plot here. So outside to the left and right of this domain with the spatially variable area sink in it, there is constant recharge rate, and that's this level portion of line here and this level portion of line here with a negative number because it's coming in the top rather than going out. In the area of this wetland or river channel, the flow direction is reversed. Water is coming up and out of the domain, and it is spatially variable. So it varies as you go across the yellow line from one side of this to the other. And it's a positive number and different. The lowest part of the river here is modeled just with a river line boundary, which has no width, and we've discussed that before.